Alright guys, we've been looking at acid-base problems, so now what I want to do is look at a KSP problem. Just like all questions from about 2013 on are all free response sections of the test from 2013 and older. Question 1 is an equilibrium problem. This equilibrium problem happens to be a KSP problem. So let's just kind of look at this and see where we end up. We have a student preparing a 100 milliliter solution, saturated solution of magnesium fluoride by adding 0.50 grams of solid magnesium fluoride to 100 milliliters of distilled water at 25 degrees Celsius. They are stirring the solution until no more solid dissolves. This is what makes it saturated. And because there's no more solid dissolving, there's solid still left over. But the volume of that solid is negligible. So in other words, we're still dealing with 100 milliliters of water. What this tells us is we have that equilibrium between the magnesium fluoride and the ions that are produced from when the magnesium fluoride dissolves. We'll get there in a minute. The saturated solution is analyzed, and it is determined that the fluorine ion in this solution is 2.4 times 10 to the negative 3 molar. So think of this almost like, it's really no different than an acid-base problem. So this is almost like saying the pH is this, or the hydrogen ion concentration is this. It all kind of works the same way. So let's kind of take this a little bit at a time. A1 tells us to write the equilibrium, the chemical equation, for the dissolving of the magnesium fluoride in water. So let's do that. We have magnesium fluoride, which is a solid, and it is going to be breaking down into its ions. That's what all KSPs are going to do. So its ions are going to be magnesium, plus 2, and the charges are important on these. You don't typically get points unless you have the charges present, plus 2 fluorines, so 2 fluorine ions. And that's where we end up. So pretty easy and straightforward. From there, it says to calculate the number of moles of magnesium fluoride that dissolved. Okay, well, that's a little bit interesting. How are we going to do that? Well, like all equilibrium problems, we're going to use an ice table to kind of work this out and see where we end up. And there's actually 2 or 3 different ways you can solve this. I'm going to work you through 2 ways. The first one is going to be the ice table, our handy-dandy ice table. Okay, so because this is solid, we don't care about it. And by the way, these are the aqueous ions. We are going to ignore the solid, but we are going to pay attention to the ions. So ICE. We assume as we're making this solution, there's 0 magnesium and 0 fluorine, which means we are adding X and adding 2X here, because remember our coefficients are going to come down. We end up with X and 2X at equilibrium. Well, we're already told that the fluorine ion in the solution at equilibrium is 2.4 times 10 to the negative 3, which means we know this value already. 2x is going to be equal to 2.4 times 10 to the negative 3. Well, what does that mean? It means x is equal to 1.2 times 10 to the negative 3. Why is all that important? Well, because if we backtrack over here and let's say we have a certain amount of this, and again, we don't typically put anything here because it's a solid, but I want you to kind of see what's going on here. If this is Z amount, whatever that amount happens to be, we know it's going to be shifting towards the products, which means this is going to be minus X, and maybe if we did a different color, we could actually see that a little bit better. Minus X, okay? X is the molarity of how much of this is going to dissociate or dissolved in this case, which means if we know what X is, we can backtrack that to our mole value for this guy. Okay, well, come over here. We know our X value because we were able to calculate it using the fact that we had 2.4 times 10 to the negative 3rd molar fluorine. Therefore, we have 1.2 times 10 to the negative 3rd X. Why is that important? Because that is our molarity, which means we can take that to moles. So remember, molarity equals moles over liter. So if we have 1.2 times 10 to the negative 3rd molar, that's going to equal X moles over our volume, which if remember we go up here, we have 100 milliliters, and the solid that's left over does not change that, so we still assume 100 milliliters, so 0.1 liters. And we can basically do that math, and what we're going to end up with is the amount of moles of magnesium fluoride that dissolves. So X, well, let's not do X, we'll call it, well, we'll just do moles. So the amount that dissolves is going to be 1.2 times 10 to the negative 4 moles. So that's kind of one way to work this out and kind of figure out what's going on. And that's the way I would choose. Let me show you another way that works just as well. Instead of doing the ice table, we can actually do some basic stoichiometry. And some of you may prefer that way over the other. Because we know the amount of ions that are produced, we can backtrack this as well. So in other words, 2.4 times 10 to the negative third molar. We want to get our mole value because of stoichiometry, so x moles over our 0.1 liters, and that's going to give us, we'll do an arrow instead of an equal sign, 2.4 times 10 to the negative fourth moles. Well, that's moles of fluorine ion. So let's look at our train tracks. 2.4 times 10 to the negative fourth moles of fluorine and fluorine ions. Do our train tracks. Look at our ratio for every 2 moles of fluorine ions. We have 1 mole of magnesium fluoride, which is what we're trying to get into. So if we do this math, we're dividing this number by 2. We end up with 1.2 times 10 to the negative fourth mole. So same answer we just got last time. It works either way. It doesn't matter which way you choose, as long as you're kind of getting the basic idea of where the math is coming from and why it is what it is. Okay, let's move on. Part 3 of A, and yes, we are still on A, is asking us to calculate the solubility product constant. So this is one reason why doing the ice table is kind of handy, is because you already have those values. So if we kind of remember back, we said 2x is equal to the 2.4 times 10 to the negative third molar, and that came from our fluorine ion concentration. And we can do our ice table again if that helps to see it. Okay, don't care. 0, 0, plus x, plus 2x, x, and 2x. And we know the fluorine ion concentration is already this, so we know that that's what our 2x is. And we know x is going to be 1.2 times 10 to the negative third. We can do that by just solving, knowing that 2x is 2.4 times 10 to the negative third. X is going to equal half that, 1.2 times 10 to the negative third. So how do we find Ksp? Well, first off, our expression, Ksp, is going to be equal to just our products because our reactant is a solid. So that's going to be the concentration of magnesium ions times the concentration of fluorine ions, and this is going to be squared because, again, our coefficients end up as our exponents in our Ksp expression. So magnesium is equal to x, which is 1.2 times 10 to the negative third. Fluorine is equal to 2x, which is 2.4 times 10 to the negative third. So Ksp is going to be equal to 1.2 times 10 to the negative third times 2.4 times 10 to the negative third squared. And when we go through and do this math, what we're going to get is Ksp is going to be equal to 6.9 times 10 to the negative 9th. So really not any different than what we've been doing with acids and bases. Okay, so we have what used to be called a reset button. So now we're completely changing gears to a new prompt. We have a beaker containing 500 milliliters of a solution in which both calcium and barium ions are present at a concentration of 0.10 molar at 25 degrees Celsius. A student intends to separate the ions by adding 0.2 molar sodium fluoride solution 1 drop at a time from a burette. At 25 degrees Celsius, the Ksp values for calcium fluoride is 3.5 times 10 to the negative 11th, and the Ksp value for barium fluoride is 1.8 times 10 to the negative 6. So what in the world's going on here? We have a beaker with calcium ions and barium ions, and they're adding sodium fluoride, almost kind of like a titration, but not quite because we're not dealing with acids and bases. The fluorine ion is pretty well insoluble with just about everything except for group 1 and ammonium, which means when it comes in contact with the calcium or the barium, it's going to precipitate out. So with that in mind, these Ksp values play a pretty big role, and this is something we kind of talked about in class, but not quite, so I want to kind of work through this real quick. If you have barium fluoride, it's going to break down into barium and fluorine ions, 2 fluorine ions, or if you have calcium fluoride, breaking down into calcium ions and 2 fluorine ions. So here's kind of the idea. As the ions build up, think of your Q value here. And remember, we're kind of ignoring the reactant side because both of these are solids. Think of your Q value here. As you're adding the fluorine ion and you already have the barium ion in here, what's going to eventually happen is Q is going to become greater than K. Which, if you remember correctly, if Q is greater than K, it means our products are too large. So we're going to end up shifting towards the reactants. Well, what happens as we shift towards the reactants? The solid starts forming. So as long as our ions stay at a low concentration level and Q remains less than K, meaning we're not at equilibrium or we're just at equilibrium, we won't ever actually see any solids. So we can have an unsaturated solution by adding the salt in, but not actually getting any precipitant. Now, as we add more salt and more ions end up building up, we end up shifting over and we end up having that solid forming. So let's look at what this question is asking with that information. Which salt will precipitate first, the calcium fluoride or the barium fluoride, and justify your answer? Well, look at your two Ksp values. We have one that's 3.5 times 10 to the negative 11th and one that's 1.8 times 10 to the negative 6th. This is significantly smaller, which means as these ions are building up, that calcium ion is going to hit Q first because K is very small. So Q is going to be greater than K first, way before barium fluoride is going to be able to reach K, which means this is going to shift towards the products before this guy, or not towards the products, sorry, towards the reactants, before this guy can shift towards the reactants. Well, what does that mean? That means we're going to see this solid first. And because we see that solid first, the calcium fluoride is going to be the one that precipitates first. So, kind of thinking about it this way, because the Ksp of calcium fluoride is so much smaller, it's going to have less ions floating around in solution, and therefore more solid is going to form or be left in solution. So these ion concentrations are going to reach your K value, or Q value, however you want to think about it, much quicker than these guys are going to, because it takes a lot more of these to hit your K value. So these guys are going to hit our K value first and then exceed our K value, so Q is going to be greater than K, causing a shift towards our reactants, causing a precipitation of CaF2 first. Okay, I'm going to go ahead and stop there. We'll come back and deal with the second and third part of B on the next video.